Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In today's video we're going to take this concept of signed areas and start connecting it with the curves that are going to be fundamental in our understanding and development of the algebraic calculus. So we're going to meet some simple but very important examples of curves without actually having a completely clear idea of what a curve is, but we may start with some simple examples. And we're especially interested in the kind of configuration that we're going to be seeing right here, where we have a curve, in this case the parabola y equals x squared, that I hope you are all somewhat familiar with, and a triangle on that curve. In other words, we're choosing 3 points on the curve. In this case, the point 1, 1, which is A, the point 3, 9, which is B, the point C, which is minus 2, 4. So these 3 points on the curve determine a triangle. And then we can consider the oriented triangle by choosing an orientation. Say A, B, C. That gives us the oriented triangle that we denote by this little circle here with a little arrow in that direction. Okay, so how would we go about calculating the signed area of this oriented triangle? Well, we know how to do that. The signed area of the oriented triangle ABC is the sum of the signed areas of the 3 oriented sides. S of AB, this oriented side here, S of BC, that oriented side, and S of CA, that oriented side there. And the individual signed areas of these things are obtained in a very nice way by just using our cross product formula. So here's the point 1, 1, and here's the point 3, 9. So we're taking the cross product of essentially the vectors 1, 1 and 3, 9. So we're talking about this point and this point here, and the formula is 1 times 9 minus 1 times 3 all over 2. So in other words, 9 minus 3 over 2. And correspondingly, the oriented side BC, there's 3, 9, and minus 2, 4. So we take 3 times 4, which is 12, minus 9 times minus 2, which is plus 18, all over 2. And finally, this oriented side here, from minus 2, 4 to 1, 1, we take minus 2 times 1, which is minus 2, minus 4 times 1, which is minus 4, all over 2. And so 9 minus 3 over 2, that's 6 over 2, that's 3. Here we have 30 over 2, which is 15. And here we have minus 6 over 2, which is minus 3, for a grand total of 15. Telling us that the signed area of this triangle is 15. So it's intuitively the same, perhaps, as a parallelogram formed from 3 this way, 5 that way. On our grid paper, that would be roughly comparable. Okay, so that's a specific example, and it's good to be able to make that kind of calculation. But what we want to do today is we want to go up a level and try to look at this kind of problem more generically, more algebraically. So replace the specific numbers that are appearing here with more general algebraic expressions, and that will reveal more structure to us. It's an important idea that we want to be algebraic. So we want to look at a situation and say, what's the algebraic essence of this? So we want to go from arithmetic to algebra, and that way we get a bigger picture, we get more information. Okay, so this curve y equals x squared that we're starting to have a look at, and curve in quotes here because we have not defined what exactly that means. That's going to be an important issue for us later on. But anyway, this curve, this graph, this physical object has a special property that it's parametrizable. That means that we can get at the points which lie on it in a relatively easy, direct fashion. And we can say that this equation y equals x squared has a parametrization t comma t squared. In other words, points of this form satisfy this equation, and things that satisfy this equation are of this form. So here the parameter is t, which is just the x coordinate. So we can describe points on the curve by this parametrization. And so, for example, we could consider 3 points on the curve, A1, which is T1, T1 squared, A2, which is T2, T2 squared, and A3, which is T3, T3 squared, for some unknown or variable numbers T1, T2, and T3. So here we can picture perhaps one possibility. There might be A1, there might be A2, there might be A3. In which case the T1, T2, and T3 values are just the x-coordinates. So if we went down parallel to the y-axis, we would get a value here, that would be T1. Go down parallel here, we get a value T2. Go down parallel here, we get a value T3. Okay, so now we have this triangle composed of these sort of generic or variable points on the curve, and we can ask for the signed area of A1, A2, A3. So in this case, the orientation would be this way. Okay, so what's that going to be? So now we're going to make the same kind of computation we did in the previous example, but now instead of having numbers, we have these variables, T1, T2, T3. Okay, so what happens? So T1 squared and T2 squared, what's the signed area of the segment that they form? Well, it's T1 times T2 squared minus T1 squared times T2 all over 2. And then going from A2 to A3, it's the same kind of thing. We get T2 times T3 squared minus T2 squared times T3, again over 2. And then finally going from A3 to A1, corresponding to that side, we get T3 times T1 squared minus T3 squared times T1 all over 2. So now we have this nice algebraic expression. We can see there's a common denominator of 2. And then the numerator will be the sum of these 6 terms, and they're all of degree 3. And pleasantly, this degree 3 expression is exactly factorizable this way. It's the product of the linear factors T1 minus T2, T2 minus T3, and T3 minus T1. So you can check that by expanding this out and seeing that you're just getting the numerator here. So very pleasant, this algebraic expression that represents the signed area of this thing here is now given to us by this expression here. And the linear factors that appear here in the numerator are very interesting and important because they alert us to the fact that when 2 of these indices or parameters are equal, then the signed area becomes 0. That's sort of obvious, right? If A2 and A3 become the same point, then our triangle is collapsing to just a segment, and it obviously should have 0 area. Okay, so now let's look at a slightly more sophisticated example where we go from a quadratic curve to a cubic curve. Let's consider the curve with equation y equals x cubed. Now that has a graph that looks something like this. If we set up coordinates like this, so 1, 2, 3 in the x direction, 1, 2, 3, and so on in the y direction. Notice that I'm using a little bit of compressed coordinates in the y direction so that the steep increase of this curve as x gets bigger is captured a little bit better. So what do we see here? We see the point 0, 0. This is the point 1, 1. This is the point 2 cubed, which is 8, 2, 8 somewhere there. And minus 1 there, and maybe minus 2, minus 8 would be down there somewhere. So those are some points on the cubic. And now let's consider a general triangle formed by 3 points on this cubic curve. And we'll do that by describing the curve parametrically this way. That t comma t cubed is a parametrization for the curve. Every point of this form, no matter what t is, will satisfy the equation because the y-coordinate is the x-coordinate cubed. And conversely, if you have a point that satisfies this equation, then it's necessarily the form t cubed, because whatever x is, namely t, then y has to be the cube of it. So this is a parametrization of the curve, and using that parametrization, we can express 3 arbitrary points on the curve in terms of the unknown values t1, t2, and t3. So we have a1, which is t1, t1 cubed, a2, which is t2, t2 cubed, and a3, which is t3, t3 cubed. And I've just sort of illustrated it by choosing some 3 particular points. But these are supposed to be generic, and then we consider the triangle a1, a2, a3, the oriented triangle formed by these 3 generic points. And we're interested in the signed area of this thing. And of course we can compute that now because we just take the sum of the signed areas of the 3 sides. So a1, a2 has signed area t1, t2 cubed minus t1 cubed t2 all over 2. And then the a2, a3 will be t2, t3 cubed minus t2 cubed times t3. And finally, a3, a1 will be t3 times t1 cubed minus t3 cubed times t1 all over 2. Okay, so now we can take the 2 as a common denominator, and then we again have 6 terms, each one now of degree 4. And now you have to kind of stare at this and say, well, is this going to factor? And it will factor, because the same kind of argument that we saw in the quadratic case will be happening here. If one of the pairs of these t values, say t1 and t2, coincide, so if t1 equals t2, it means that 2 of our 3 points are coinciding and the triangle is collapsing to a degenerate segment, and the area must then necessarily be 0. That's telling us that the factor t1 minus t2 ought to be a factor of the expression that we're getting here. So we can expect, just on the grounds of this argument of collapsing of areas when we have collinearity, that the t1 minus t2 factor, the t2 minus t3 factor, and the t3 minus t1 factor, they ought to be factors of this expression. So once we know that, or have an idea about that, then we can verify that that actually is true and that there's an additional linear factor, because the whole thing has to be of degree 4. And the other linear factor turns out, pleasantly, to be just the sum t1 plus t2 plus t3. We do expect that there's going to be some linear factor there. Actually, maybe it's not that surprising. If it's linear, it ought to really be sort of symmetric in t1, t2, t3. So at least up to a multiple, we are not surprised by getting that. In any case, it's still a very nice expression, and it's telling us a nice formula for the area of a triangle, oriented triangle, formed by 3 general points on this cubic curve. Now we can extract from that very nice formula a very pleasant and interesting geometrical understanding that tells us when 3 points on the cubic are collinear. So the points t1, t1 cubed, t2, t2 cubed, t3, t3 cubed on y equals x cubed, on our curve that we're considering, if distinct, they are collinear precisely when t1 plus t2 plus t3 equals 0. Because the collinearity is equivalent to the signed area being 0. And we have that nice factorization of the signed area's numerator. So that's going to be 0 precisely when one of those 4 factors is 0. And if t1, t2, and t3 are distinct, in other words, if we have 3 distinct points, then the first factors, t1 minus t2, t2 minus t3, and t3 minus t1, they're never going to be 0. So it's only going to happen when the 4th factor, t1 plus t2 plus t3 equals 0. So for example, here in this diagram, we see the points 2, 8, and here's the point minus a half, minus 1/8, and here's the point minus 3/2, and it's cubed minus 27 over 8, somewhere between 3 and 4. So these points on the cubic are in fact collinear because the sum of the parameters, which are just the x-coordinates, 2 plus minus a half plus minus 3/2, is in fact 0. Okay, so this opens up a very interesting geometrical investigation that turns out to be very rich. The study of collinearity of points on cubic equations more generally. So this turns out to be a very rich subject, and we will be able to say things in this direction as we proceed. But so we already see that this signed area formula for triangles is telling us something that's interesting geometrically, and that's not entirely obvious in the case of the cubic curves. Now let's look at the same kind of question, but with another important curve, what's usually called the unit circle, okay, which figures very prominently in calculus. So the unit circle is given by this equation: x squared plus y squared equals 1. And there's a familiar graph with the x and y axes, in this case, labels so that this segment here and this segment here are to us visually equal. Otherwise we would get something that looks more like an ellipse. Okay, so this is a sort of familiar unit circle, x squared plus y squared equals 1, describing that curve. Okay, and now we need to touch base with a very important parametrization of this curve. So this curve also has a parametrization, but it's not the cosine theta, sine theta parametrization that you may have studied in high school. You have to let go of that. So here we're going to use the much more important rational parametrization of the unit circle, which I talk a lot about in my videos. It's absolutely fundamental kind of understanding of the circle. Okay, it's sort of like one of the first things that you really ought to know about the circle, is that a typical point on it can be described by these two numbers: 1 minus t squared over 1 plus t squared, and 2t over 1 plus t squared. So that's a point that always turns out to be on the unit circle. That's something that the ancient Greeks knew. In fact, the Babylonians knew about it 1,000 years earlier than the Greeks did, at least. So let's denote by this particular point, let's call it e of t. Okay, so we're giving it a name. And we'll see in the worked examples, if you haven't already understood this from other of my lectures, that this point e of t can be described geometrically in a very nice way with this diagram here. So here's the point -1, 0. And here is the point on the y-axis with coordinate t. So in this case, t might be, 0.4 or something like that. And you join this point with that point, and where it meets the circle in the second point, that turns out to be e of t. So that shows geometrically what the dependence of the point e of t on the point or the number t is. Okay, so let's just adopt that rational parametrization. We'll talk about that and derive it in the worked examples or worked problems. And now let's choose 3 points on the circle in terms of this parametrization. So we'll let AI be e of ti, where I runs from 1 to 2 to 3. So we're taking 3 parameters, t1, t2, and t3, and considering the corresponding points that you get by plugging in t1, t2, and t3 into this formula. So we get 3 points on the circle. Let's picture them here, a1, a2, a3. And so we get a triangle. If we choose the orientation, a1, a2, a3, then we have an oriented triangle. And we'd like to calculate what the signed area of this thing is. Okay, so now it's an interesting calculation. Not so easy if you do it by hand, but not so hard if you have a little bit of help from a computer. So again, we just go through the 3 oriented sides one at a time, compute the signed area of each of the oriented sides and add them together. And then you have to take that rather big expression and you have to simplify it algebraically. And what you get, it turns out, is this. Okay, a very beautiful formula, which has this now familiar factorization in the numerator, t1 minus t2, t2 minus t3, and t3 minus t1. We're no longer surprised that that occurs because we know that if 2 of these points coincide, then the area is going to resort to 0. But what's not so obvious is what else there is in this formula. There's also a 2 in the numerator, and then there are these 3 quadratic factors in the denominator. t1 squared plus 1, t2 squared plus 1, t3 squared plus 1. That's just what you get when you examine the algebra of the formula for the signed area of this generic triangle formed by points on the unit circle. So it's a very pleasant formula, very beautiful, I think, and it's an algebraic manifestation of geometry, right? We're looking at something geometrical, the area of a triangle inscribed in a circle, and we're expressing that algebraically in terms of the parameters that specify those 3 points. Now, another curve that's going to be playing a very important role in calculus is this one here. The curve y equals 1 over x, which is a hyperbola. Typically looks like that. Or we could also rewrite the equation by just getting rid of the denominator there and writing it as x times y equals 1. That's no longer as a function, y is a function of x, but in fact it's a kind of preferred algebraic expression because it doesn't have fractions and it's treating x and y more symmetrically, which is really what's happening. Okay, so either way, this very important curve has a parametrization t comma 1 over t. So if x is t, then y is 1 over t. That's a parametrization. And so we can find 3 points, generic points, by just using 3 different values. So a1 is t1, 1 over t1, a2 is t2 and 1 over t2, and a3 equals t3 and 1 over t3. And then it's a relatively simple exercise to show that the signed area of the triangle a1, a2, a3, again obtained just by taking the sum of the 3 signed areas of the segments, turns out to be simplifiable to the following expression. t1 minus t2, t2 minus t3, t3 minus t1, that now familiar expression in the numerator. But in the denominator, 2 times t1 times t2 times 3. 2 times the product of the 3 parameters. That's also a very nice formula. Okay, so yeah, so this is a very interesting kind of thing. Now we see that we could, in principle, ask this kind of question for very general kinds of curves. As long as we have a parametrization for a curve, then we can ask, well, what does the signed area of a general triangle on this curve look like in terms of those parametrized values? And we're going to end the lecture with one more example, another example of an important curve that figures very prominently in calculus. So we're meeting for the first time, essentially, some important curves here, along with some new or newish formulas for areas of triangles associated to curves. So this third example of a curve is also very important for calculus. But it's a little bit more complicated in some ways. It's not actually a function like the 1 over x curve that we looked at just previously. It's a little bit sharing features with the unit circle because it has the equation that's very similar to it. So it's x squared minus y squared equals 1, okay, which is a hyperbola. And okay, so I'm graphing like this. As usual, I'm not exactly making perpendicular axes. If these axes look a little bit not perpendicular to you, I'm doing that a little bit on purpose, just to alert you subconsciously that we do not actually need the usual Cartesian story where we have exact perpendicular axes with exact squares, a grid square. No, we don't need that. We're working in a more flexible affine situation here. Okay, so here's an x-axis, y-axis, some labelings there, and here is this curve, and it's perhaps useful to orient it with respect to 2 lines which are very important. These are the asymptotes, this line here and this line here. This is the line y equals x, and this is the line y equals minus x. Okay, and it turns out that these are the lines that this hyperbola sort of meets as we go further along in these branches. It approaches these 2 lines. So from far away, this hyperbola just almost looks like a pair of lines. except near the origin it has this sort of rounded aspect. In any case, it turns out that this curve also has an affine parametrization, just like the circle did. In fact, the formula for it is very similar to the circle formula. So here's the affine parametrization of this hyperbola. It's, let's call it f of t. It's 1 plus t squared over 1 minus t squared and 2t over 1 minus t squared. Okay, so there's a lot to say about this, and we will be talking more about it. And in the worked problems, we'll get some more familiarity with this. But it has a similar kind of interpretation geometrically as it did for the circle. If we choose the point minus 1, 0, and choose the point on the y-axis with coordinate t, then this line generated by these 2 points will meet the hyperbola in a second point, and that will be f of t. So that shows the dependence geometrically. You vary the t value, then this line will vary and will meet the curve in different points. If t happens to be up here, for example, then the line that we're talking about would be something like this, and it would meet the curve at a point something like that one down there. So we do get both branches using this parametrization. Okay, so algebraically though, we can just proceed as we have for the circle or the other hyperbola. We can choose 3 points, a1, a2, a3, by simply replacing the t here with 3 variable values, t1, t2, and t3. So we get 3 different points on the curve. And we call those a1, a2, a3. There's an example. And then we're interested in the signed area of that oriented triangle. And again, we have to make a calculation that's very similar to the calculation for the unit circle case. And it's algebraically a little bit sophisticated. And we get an expression that looks very similar to what we got for the unit circle. We get 2 times the product t1 minus t2, t2 minus t3, t3 minus t1, over the product t1 squared minus 1, t2 squared minus 1, t3 squared minus 1. So just the same as for the unit circle, except that there are minus signs here in the denominator instead of plus signs that we had there. Corresponding, perhaps, if you like, to the fact that the only difference in the equation is having a minus sign there instead of a plus sign. Okay, so I think this opens up all kinds of interesting questions. What happens with more general curves? If we choose other curves whose parametrizations we happen to know, then we could, at least in principle, ask the same kinds of questions and derive similar, perhaps more complicated, formulas for the areas, signed areas of triangles on these curves. So this is a nice connection between our initial foray into setting up area and the geometry of some important but relatively simple curves that are going to figure very prominently in the calculus. So there's much to learn. I'm Norman Wahlberger, and thanks for listening.